Hi all, welcome to the video. In the last video, we discussed about the diagonalization of symmetric matrices. Here I am going to discuss the diagonalization of non-symmetric matrices. This is the first problem. Diagonalize capital A equal to 600, 1220, 21 minus 6, 9. First of all, let me check this matrix is symmetric or not. Here A transpose is equal to 6, 12, 21, 0, 2 minus 6, 0, 0, 9, which is not equal to A. Therefore, this matrix is not symmetric. Then moving to finding the eigenvalues. This is a 3 by 3 matrix. So this has 3 eigenvalues. Here, first of all, check this matrix. Here, the elements above the diagonal elements are all 0 because this is a lower triangular matrix. Okay, lower triangular matrix because the elements above the diagonal elements are all 0. We have a result for a triangular matrix. It may be upper or lower, and for a diagonal matrix the eigenvalues are its diagonal elements. Eigenvalues are the diagonal elements. So here this is a triangular matrix. So this matrix's eigenvalue will be, that is lambda equal to 6, 2, 9. Because this is a lower triangular matrix, so the eigenvalues will be the diagonal elements. Let's see. First of all, we are going to write the characteristic equation. So this is the characteristic equation, that is lambda cube minus 17 lambda square plus 84 lambda minus 108 equal to 0. Solving this, we got lambda equal to 2, 9, 6. These are the elements in the diagonal. Okay, 6, 2, 9. So this is the diagonal elements. Next, we are going to find the eigenvectors corresponding to this eigenvalues. First of all, for when lambda equal to 2. So the eigenvectors are finding by solving this equation A minus lambda I into x equal to 0, which implies here lambda equal to 2, then the matrix will be 4, 0, 0, 12, 0, 0, 21 minus 6, 7 into. This is a 3 by 3 matrix. Okay, so we have 3 variables, that is x1, x2, x3 equal to 0. Here we are solving this by finding the rank. So I am interchanging the first and third row. So R1 interchange to R3. We have the matrix 21 minus 6, 7, 12, 0, 0, 4, 0, 0. Here the first non-zero element is 21. So we want to make this 12 as 0 and this 4 as 0. The transformation is R2 changes to R2 minus 12 by 21 R1 and R3 changes to R3 minus 4 by 21 R1. Then the matrix will be 21 minus 6, 7, 0, 24 by 7 minus 4, 0, 8 by 7 minus 4 by 3. Okay, then moving to the next row, that is second row. Here this is the non-zero element. We want to make this element as 0. The transformation is R3 changes to R3 minus 1 by 3 R2. That is R3 changes to R3 minus, the element in the R3 is 8 by 7 divided by element in the R2, that is 24 by 7 with respect to R2. So this is R3 minus 7, 7 cancel, that is 1 by 3 R2. So this is the transformation. Then we want to make this 8 by 7 as 0 like this. Then this matrix is a upper triangular form. Next, we are moving to find the rank. Here rank is equal to the number of non-zero rows. Here it is 2. Here rank equal to 2 and number of variables is equal to 3. So this system has infinitely many solutions. So put arbitrary values to n minus r variables. By back substitution, we have these solutions. That is, here the solutions is x1 equal to 0, x2 equal to 7 by 6 t, x3 equal to t. This is got by solving the equations. From the final matrix, by back substitution we have 21x1 minus 6x2 plus 7x3 equal to 0, and from the second row we have 24 by 7 x2 minus 4x3 equal to 0. Here we want to put one variable, an arbitrary value, so put x3 equal to t. x3 equal to t. When x3 equal to t, the second equation will be 24 by 7 x2 equal to 4t. So x2 will be 4t divided by 24, then here into 7. So this is equal to 7 by 6t. So x2 equal to 7 by 6t. Putting these values in the first equation, we have x1 equal to 0. So this is the eigen vector corresponding to lambda equal to 2. So here this is 0, 7t by 6t. Here this is a fractional value. Then that is taking t outside, that is 0, 7, 6. Therefore the first eigenvector is 0, 7, 6. Next, when lambda equal to 6, this will be the matrix. Here I am going to interchange R1 and R3. Then the matrix is like this. Then next we want to make this 12 as 0. For that the transformation is R3 changes to, not R3, R2. R2 changes to R2 minus 12 by 21 R1. Okay, this is the transformation. So this becomes 0. Next element minus 4 by 7 minus 12 by 7. This is an upper triangular matrix. Then by back substitution we have two equations. Here also rank is equal to 2 and n is equal to 3. So we want to put n minus r variables an arbitrary value. Here the by back substitution, here the equations are 21x1 minus 6x2 plus 3x3 equal to 0, and minus 4 by 7 x2 minus 12 by 7 x3 equal to 0. When we put x2 equal to t, then we have x3 equal to minus t by 3 and x1 equal to t by 3. Therefore the eigenvector will be this one, that is x2 equal to 1, 3, minus 1. Next, one more eigenvector is remaining when lambda equal to 9. This is the matrix. Here also interchanging the first and third row, and transformations is R2 changes to R2 minus 12 by 21 R1, and R3 changes to R3 plus 1 by 7 R1. Next, one more transformation, R3 changes to R3 minus 6 by 25 R2. This will be the matrix. Here rank is equal to 2, n is equal to 3. From this we have x2 equal to 0 and x1 equal to 0. So put x3 equal to 3, which means here by back substitution we have 21x1 minus 6x2 equal to 0, and from the second row 24 by 7 x2 equal to 0. From that we have x2 equal to 0. When x2 equal to 0, the first equation will be x1 equal to 0. One more variable is remaining, that is x3. So put x3 equal to t. Then the eigenvector will be 0, 0, t. T taken as outside, the 0, 0, 1. So the third eigenvector is 0, 0, 1. Next, we are going to diagonalize this matrix. Here the matrix is not symmetric. Therefore, the diagonalization D equal to P inverse AP, where P equal to the first column corresponding to the eigenvectors of x1, second row x2, third row x3. So this will be our first eigenvector x1 is equal to 0, 7, 6. So write the elements in the column wise. So 0, 7, 6. x2 is 1, 3, minus 1, and x3 is 0, 0, 1. Then after finding P inverse and then multiplying P inverse into A into P, we have a diagonal matrix with the diagonal elements as 2, 9, 6. So this is the diagonalization of not symmetric matrix. One more problem, diagonalize the matrix A equal to 1 minus 3, 3, 0 minus 5, 6, 0 minus 3, 4. First of all, find A transpose, then check is it symmetric or not. Here this is not symmetric matrix. Okay. Then find the characteristic equation. Here the characteristic equation is lambda cube minus 3 lambda plus 2 equal to 0. Solving this, we have lambda equal to -2, 1, 1. Next, find the eigenvectors corresponding to these eigenvalues. When lambda equal to -2, a minus lambda I into x equal to 0 will be this one. Here, R3 changes to R3 minus R2 because here the first non-zero element is 3. Below elements are 0. So moving to a second row, first non-zero element is -3. So we want to make this -3 as 0. For that, the transformation R3 changes to R3 minus R2. So this will be an upper triangular matrix. Here rank is equal to 2 and n is equal to 3. Infinite number of solutions. By back substitution, we have minus 3x2 plus 6x3 equal to 0 and 3x1 minus 3x2 plus 3x3 equal to 0. Put x2 equal to t. Then solving these two equations, we have x3 equal to t by 2 and x1 equal to t by 2. So the first eigenvector is 1, 2, 1. Similarly, when lambda equal to 1, the matrix is like this. Here, the first non-zero element in the first row is -3. So we want to make this -6 as 0 and this -3 as 0. So the transformation is R2 changes to R2 minus 2 R1 and R3 changes to R3 minus R1. So this is the matrix. Here rank is equal to number of non-zero rows, that is 1, and n is equal to 3. Then infinite number of solutions. So put arbitrary values to n minus r variables, that is 3 minus 1, that is 2. By back substitution, we have minus 3x2 plus 3x3 equal to 0. Only one equation. So substitute x1 as a and x2 as b. Then substituting in this equation, we have x3 equal to b. In another way, we can substitute x2 equal to a and x3 equal to b. But when we substitute like this, we have no idea about x1 because here in the equation x1 is absent. So this is not a possible way. So substitute x1 equal to a, then any other variable as b, whether x2 equal to b or x3 equal to b. When x3 equal to b, from the equation we have minus 3x2 equal to minus 3b. So x2 will be b. This is another possible way. So here we want substitute either x1 equal to a and x3 equal to b, or x1 equal to a and x2 equal to b. Therefore the eigenvector is a, b, b. Splitting this, that is a into 1. Here in the second element there is no a, so 0, 0 plus b into first element is 0, 1, 1. Here we take the next eigenvector x2 as 1, 0, 0 and the another eigenvector x3 as 0, 1, 1. So here we have 3 eigenvectors. Corresponding to this eigenvalue, we have 2 eigenvectors. So totally 3 eigenvectors which are linearly independent. This is a not symmetric matrix. So D equal to P inverse AP and P equal to like this. Directly writing the elements from eigenvector x1, x2, x3, we have P equal to 1, 1, 0, 2, 0, 1, 1, 0, 1. Finding P inverse and multiplying with AP, we have a diagonal matrix with the diagonal elements as the eigen values. So minus 2, 0, 0, 0, 1, 0, 0, 0, 1. So this is the diagonalization form of this given matrix. These are some exercise problems.